We can determine the gravitational field of a distribution of mass by summing the contributions from tiny bits of mass in the distribution. In the limit that these bits of mass are infinitesimally small, this summation becomes an integration. For example, let's calculate the gravitational field of a uniformly dense rigid rod a distance d away from one end of the rod. We can model this rod as a combination of infinitesimal bits of mass that we model as point particles. The mass of each of these point particles is denoted by dm. The infinitesimal gravitational field of each point particle is found using the equation for the gravitational field of a point particle. The gravitational field of each point particle points in the negative r hat direction for that point particle. Thus, the net gravitational field of the rod at position P points toward the rod. The smallest value for the variable r in this equation for the gravitational field of each point particle is d. In other words, the closest any point particle in the rod can be to position P is d. The largest value of r is d plus L. The total gravitational field of the rod is the integration of the contributions from each point particle in the rod. Let's define an x-axis for this system with a positive direction pointing from the rod to the position P. In other words, the positive direction for the x-axis points to the right in the figure. Since the direction of the gravitational field at position P is towards the rod, the direction of the gravitational field at position P is in the negative x-axis direction. As shown previously, we can express each infinitesimal bit of mass in the rod in terms of the rod's linear mass density and an infinitesimal bit of length along the rod. Since the rod is uniformly dense, its density is constant and can be taken outside the integral. The gravitational constant and the x hat unit vector are also constants. The resulting integration is straightforward. We arrive at our final expression by substituting the equation for the linear mass density of the rod. We can also determine the gravitational field from the gravitational potential. The negative sign in this equation indicates that the gravitational field always points toward lower gravitational potential. For example, we can calculate the equation for the gravitational field of a point particle from the equation for the gravitational potential of a point particle. Similarly, since we have already calculated the gravitational potential of a rigid rod, we could have used that expression to determine the gravitational field of a rigid rod. As expected, the results of this calculation are the same as that derived previously. Next, let's calculate the gravitational field of a uniformly dense square. This gravitational field is the integration of the gravitational fields of each infinitesimal bit of mass in the square. As discussed previously, a thin rod is a convenient shape to use in this calculation. This is the equation for the infinitesimal gravitational field of each thin rod in the square. Based upon the definitions of the x-axis and y-axis in our system, this gravitational field points in the negative y-axis direction. In other words, the gravitational field at position P points towards the rod and thus towards the square. The closest any rod in the square can be to the position P is d, and the farthest is d plus L. Thus the limits of the integration in our calculation are from d to d plus L. The gravitational constant and the y hat unit vector are constants and can be taken outside of the integral. Now, since the square is a two-dimensional object, we relate the infinitesimal bit of mass in each rod to the infinitesimal bit of area of each rod using the surface mass density of the square. Since the square is uniformly dense, this density is constant and can be taken outside the integral. We can then substitute into this expression the equation for the surface mass density of the square. Performing integration gives us the final expression.